Gravity dictates the shape of the cosmos, yet remains a total outlier in physics. Every other force of nature is defined by a specific particle. Gravity is the only one missing a confirmed quantum foundation. We have already cataloged the building blocks for the rest of reality. Electromagnetism runs on photons. The strong force uses gluons, and the weak force operates through W and Z bosons. These particles aren't just theoretical. We have measured them and even photographed their effects in high-energy labs. But the fourth column, gravity, is empty. Its proposed particle, the graviton, has never been detected. There is no photo, no signal, and until recently, no proof it even exists. Mid-century physicist Freeman Dyson attempted to bridge this gap by calculating the requirements for a graviton detector. He wanted to find the exact threshold where a machine becomes sensitive enough to catch a single quantum of gravity. His findings revealed a massive contradiction. Because gravitons are so weak, a detector must be incredibly heavy to register an impact. Dyson showed that a machine with enough mass to detect a graviton would be so heavy that it would collapse under its own weight, forming a black hole before the experiment could even begin. Under these rules, the universe effectively hides its smallest parts behind its most massive ones. The very laws of physics create a self-shielding barrier that prevents us from observing gravity's quantum nature directly. In 2024, researchers proposed a way to bypass this black hole limit. Instead of building a tiny subatomic sensor, they realized they could catch a graviton by scaling a quantum system up to the size of a human. The design centers on a massive cylinder of beryllium or niobium metal, ranging in weight from 15 kilograms to 10 tons. By cooling this cylinder to near absolute zero, scientists can stop the internal motion of its atoms. In this frozen state, the entire 10-ton mass begins to vibrate as a single giant quantum particle, making it millions of times more sensitive than a lone electron. This massive net waits for a signal from the deep cosmos, like the collision of two neutron stars. That impact sends a gravitational wave across the universe, eventually washing over the frozen cylinder in an underground lab. To confirm the signal, physicists use coincidence detection. They only count a click in the cylinder if the LIGO observatory catches the exact same gravitational wave at the exact same frequency and second. This cross-reference filters out local vibrations, leaving only the signal from the stars. By synchronizing our largest observatories with these supercooled cylinders, we can force an interaction with the universe's most elusive particle without triggering a gravitational collapse. This approach mirrors the logic Albert Einstein used for the photoelectric effect. He showed that when light hits a metal plate, it causes electrons to click out, proving that light arrives in discrete particles called photons. However, a discovery in 1968 by Willis Lamb and Marlon Scully revealed that a click doesn't actually prove the presence of a particle. They found a way that a detector can be completely deceived. This is the semi-classical loophole. In this model, light isn't a particle, it's a smooth, continuous wave. As that wave hits a quantum detector, it doesn't strike all at once. It slowly loads energy into the system over time, gradually increasing the probability of a reaction. When the energy finally hits a breaking point, the detector jumps to a new state and registers a click. To an observer, this looks identical to a particle strike, even though the incoming wave was completely smooth and continuous. This same trap applies to our 10-ton cylinder. Even if we get a perfect coincidence match with LIGO, we can't be sure if we caught a single graviton or if a smooth, classical gravitational wave simply tricked our sensor into clicking. Despite our engineering, the true nature of gravity remains ambiguous. The universe provides a signal, but hides the evidence we need to confirm its quantum origins. In 2025, physicist Ralph Schutzhold proposed a final solution to close this loophole, the optical Weber bar. This setup replaces the metal cylinder with a precise arrangement of laser pulses. The strategy relies on preparing the laser light in a noon state. This is a specific quantum setup where the photons exist in a superposition, occupying two different states or paths simultaneously. This creates a detector that functions with a logic that classical, non-quantum waves cannot replicate. This is where energy conservation becomes the key. When a gravitational wave passes through this superpositioned light, they exchange energy. To keep the math balanced, that exchange forces the gravitational wave to adopt the same properties as the light it touched. The entire gravitational ripple is forced to enter a superposition itself. This interaction provides the smoking gun. A classical, smooth wave is physically incapable of existing in two states at once. If we observe this specific superposition in our laser lattice, it proves the wave is composed of gravitons, closing the setting classical loophole for good. The scientific community has already outlined 5 specific milestones to reach this goal. We are currently refining the sensor sensitivity and temperature controls needed to execute these tests within the coming years. Proving the existence of the graviton would suggest that the fabric of spacetime is a network of quantum information. It would indicate that our physical reality is built on a foundation of discrete bits, finally providing a clear look at the mathematical structure that holds the universe together.